Okay, so we have done all of this work with exponential equations and logarithmic equations. Okay, some of it may seem like just different. Okay, logarithms are kind of a whole different world, but they're actually very useful. Okay, there's a lot of different things that happen in the world that can be modeled exponentially, whether it's exponential growth, exponential decay, and then we're also going to look at a model called logistic growth, where something starts out exponential but then kind of flattens out. But before we talk about those, now that we had all that practice yesterday solving logarithmic and exponential equations, I want to go back to those investment problems, PERT, if you will. Okay, so when we talked about investing money or car loans, we always found like the amount after so many years, correct? So I want to take a step back and I want to look at a problem where we know the amount, but we want to know that we want to find out the time it takes for us to get there. Okay, so how long will it take an investment of $1,000 to double if we have an 8% interest rate? And first of all, we're going to look at when it's compounded quarterly. Okay, so first of all, what is that formula? Well, let's just in general. A equals okay, some of us should probably look at that before Friday's test because I'm not giving you that on Friday's test. Okay? All right, so in this information, what is A? Okay, we are ending with $2,000 because we want our money to double. We are beginning with how much? 1,000, so that's P. Our rate? 0.08. N? Quarterly is 4 times a year. And then we're finding out the time. Okay, so since our variable is in the exponent, we have to get that piece by itself before we can rewrite it. So what should our first step be? Divide by 1,000. Should I leave this as 1 plus 0.08 over 4?
No.
We can probably rewrite that as what? Stop using your calculator. What's 0.08 divided by 4? Thank you. Okay. Now we have a base raised to an exponent. It is isolated. How can we rewrite this? Log base 1.2 of 2 equals 4t. You're going to have to use the change of base formula for this. And then with that answer, what are you going to do with it? All right.
So log 2 divided by log 1.02 equals divided by 4 equals.
Seth, what were you saying?
8.751 equals P.
751? And T represents?
8 years. Year.
Okay,
Almost
8 years and like 9 months, right?
Okay, if we had that question, can we just leave it like 8.01
Yes.
years?
Yes,
Not
that would be
like
fine. This would be an appropriate answer. Okay, now let's talk about what if we compound continuously. First of all, okay, yes, we're talking about PERT. Before we calculate our time, is it going to take more or less time for our money to double? Less. We make more money the more times we're compounded in a year. So if we're compounding continuously, it should take less time to get to $2,000. So amount was $2,000. We started with 1,000, and our rate was 0.08. Okay, so to solve this equation, first step, divide by 1,000. Okay, now what can we do? Okay, we're going to rewrite it. Since this is base E, we have log base E, or natural log of 2 equals 0.08t. Okay? Do you get that when you type it in your calculator?
Yes.
Okay? And does our answer make sense? It took less time. We said that that should happen, right?
Yes.
Okay. Excellent. Now what I want to talk about are those growth models and decay models. Okay? Oftentimes things happen in the world that grow exponentially. What is that going to look like? This right here. Y equals AE to the BX. We know it's exponential growth because what is its?
B.
B is positive. Okay? Things that grow exponentially. Okay. Money, that was something besides money since we just did that. Bacteria. Actually, the Ebola virus was spreading exponentially at this time last year. Scary to think
Yeah, I
about.
remember we had a little problem.
Yeah.
So what is it?
Now, all right, I'm going to cut you off. What does Y represent? The amount after so much time has passed. What does A represent? Very good. Initial amount. And B is in the place of?
Time. I
Mm,
don't know.
what's the other one?
Rate.
Our rate. Okay, X, oftentimes you're going to see that as a T instead, because that's going to be the time. Okay, so our Y and our X, those are our variables. A and B, those are constants that we need to identify. Okay, exponential decay, that's going to look like,
The opposite.
what is opposite?
Slow.
This is not linear. Not slow.
Upside down. The power is negative.
The rate, there we go. Okay. I knew you were trying to go, Seth, but I wanted us to use the correct terminology. So, we have a negative rate now. Everything else is the same, but now we have a negative rate. Do you want to miss notes? Okay, and then our last model is the logistic growth model. Okay, this is kind of cool, in my opinion. Basically, okay, do you see how this starts to grow exponentially and then it tapers off? Okay, so what I want you to think about is something like a rumor spreading. And if we calculate the number of students that hear a rumor in this school, how many students are in the school?
2,000?
Like 1,400.
I would say it's closer to 1,600.
Yep.
Okay, each class is around 400. So let's just say there's 1,600 students in this school, and I tell you something. I tell you a rumor. What are you gonna go do?
Go tell Carly.
You're gonna go tell your friends, and your friends are gonna tell their friends, the people in class. Okay, and what's gonna happen? It's gonna spread pretty quickly, right?
Spread exponentially.
Okay, it's gonna spread exponentially, but eventually, so many people are gonna hear it.
No one else.
Well, first of all, other people have already heard it,
Then it's gonna.
so it's gonna slow down. And what is the maximum number of people in the school that could hear it? 1,600. So it's going to spread really quickly, but then there's going to be less and less people to hear it. Right? So it's going to kind of taper off as far as how many people have heard it. Okay? So that's what logistic growth is.
So would that be an asymptote or that's
It is an asymptote, yes. Yes. Okay? And any problems we're gonna do like this, I'm gonna give you the formula and we're just going to work with it, okay? But there are going to be some problems where we have to write our own exponential growth or exponential decay model, okay? So we're gonna do that. Okay, if any of you go to study biology in college, a lot of experiments, a lot of research, they work with fruit flies. I find it disgusting. Fruit flies are gross to me. But fruit flies, they have very short lifespans. Okay? So in this experiment, a population of fruit flies, they notice that it's increasing exponentially. Okay, so they want to write a model for it. Well, on day 2, there's 100 flies, and day 4, there are 300 flies. How many flies after day 5? Okay, so first of all, it's growing exponentially. What's that model?
What are you gonna use for the?
Okay, very good. Now, just since we know that we're talking about time is in days and it's growing at a rate, is it okay if I change this to RT? Will you be okay with that?
Yeah.
I think R as a rate makes more sense and T as time makes more sense. T is just going to be our independent variable and Y is our
So why
dependent.
didn't they change it for this one? Why did they switch it to being
Well, just as in general, because we're used to seeing things as Y and X. Okay. All right. So what do we know? We know that after 2 days there are 100 flies. So what would that look like?
100?
Rate times 2.
Yeah.
So I'm going to write 2R instead of R2. Is that okay? All right. And we also know after 4 days there's 300 flies. So there's 300 flies after 4 days. We need to identify A and we need to identify our rate. Those are our 2 constants. Y and T are our variables. So how are we going to do that?
Can't you like say the initial could be 100 and then the final could be 300? So you do like 300 equals 100 e to the RT, and then you take the time to get that.
Okay, but what if I wanted to know like how many there were on day 1? Would that be helpful? The model that you're talking about?
Yeah, then you can find the rate and then plug everything back in.
Okay, but we need A. A is our initial time when T is 0, right?
We need to get details, so. But not yet.
Think of a different letter up there. Okay, we have 2 equations with 2 unknowns, right? So can we solve for A here?
You know,
That over there.
And then if we plug that in for A over here, then this equation is all in terms of R. Right? Can we solve for R? Yes, Ms. Holman, we can. Okay? So this is 300 equals 100 times e to the what power? 2r. We subtract our exponents when we divide. Then we can divide by 100. And then natural log of 3 equals 2r. So r is the natural log of 3 over 2. .5493. Is that what it is?
Yep.
Okay. So we have our rate. That's good. We need the rate. By the way, this population is growing at a rate of 55%. That's really fast. Okay. Now, how do we find our initial amount? Plug it back in. Look, you've already solved for A here. Now, we've rounded off right here. If we plug a rounded answer and then round again, that answer is not going to be very accurate. So please let me show you something in your calculator. You took the natural log of what?
3.
And divided it by 2. And now you need to plug it into 100 divided by e to the 2 times r. Instead of writing 2 times 0.54393 or whatever that is, if you push, you can either arrow up and hit enter, okay, and it'll call that number. If you have an 83, that's not going to work for you. So if you have an 83,
Stay in the button.
so 100 divided by e to the 2 times. Second answer calls up your last answer.
Wow, that's not gonna work. 100.
What? You got a question? Okay.
Mine didn't do that. I got 0.4 or 4.
This is because you didn't do this right. The natural log of 3, close your parentheses, divided by 2. Okay, so our initial amount is 33.3 repeating, correct?
How do you have a third of a fly?
Exactly, right? So with real data, okay, are our numbers always going to be nice?
No.
No, okay?
Mine's not working.
So this is our model. How are we going to find the number of flies after 5 days? Well, that's where mine is.
Oh, okay.
Okay, so when you plug in 5, after 5 days, how many flies are there?
You have to plug in 13.
Okay. 500 and what?
519.5.
519.59.
I got 5, 4.
Or, I mean, how many flies are there going to be? About 520?
520.
520.
Okay, I got that.
Okay, do we all get that? Okay, so you are going to have to exercise a little bit of patience through this problem. Okay, set up your 2 knowns. If you don't get an initial amount right away, you're going to have to do some substituting. Okay. Now, if they said when time is 0, the population is this, that would be nice. But that might not always be realistic in the data that's given to you. Okay. All right, one more example. Okay. On a college campus of 5,000 students, one student comes back from vacation with a contagious and long-lasting virus. The spread of the virus is modeled by this.
Yes, they give us a.
What kind of model is this?
Takers off. It's the third one.
That's that logistic growth. Let's think about it. A virus is spreading on campus. If we're just talking about the students on campus, okay, it's going to spread really fast, but then the more people that have been exposed to it, the less new people can get it. So it's going to grow exponentially and then slow down. Yes.
But like the exponent of the rate is negative.
It's in the denominator.
Okay, so like.
So remember when we had exponents in the denominator? When we move them up to the numerator, they're positive.
Okay.
Okay, so it's negative because our exponent is in the denominator. Does that make sense?
Yeah.
Okay, notice how this 5,000, that correlates to like the maximum number of people that can get it? You see what I'm saying? Okay, anyway. First of all, how many students are infected after 5 days? What are you going to do? Plug in 5. Please do that in your calculator. Now, when you are doing that, notice how your denominator has more than one term. So, you may need to put it in parentheses if you don't use your fraction button. You got 54?
Yeah.
Like exactly?
Yeah, 54.
No, yeah, 0.01.
That's a lot of people to get sick in 5 days, don't you think? One person is sick, 5 days later, 54.
Wait,
Now, back up to the problem, the college will cancel classes when 40% or more of the students are infected. Okay, so what is 40% of campus? So 40% of 5,000 is 2,000. So what are we going to do with that 2,000? Plug that in for y. So 2,000 equals 5,000 over 1 plus 4,999 e to the negative 0.8 times 5. Whoops, sorry, t. I was tapping up there. All right, we need to solve for t, which means we need to isolate e to the negative 0.8 t. So what's our first move? Multiply that denominator over. Then what? Okay, we can divide by 2,000. Which would be 2.5, right? 5,000 divided by 2,000, 2.5. Okay, next step.
why is it 4,999?
That's the model. There's a lot of calculus involved to come up with the model. No. Okay, now what? Okay, so I'm just going to write 1.5 divided by 4,999. You can do that in your calculator. And then we're going to rewrite this to the natural log of that number. So what you can do is use your second answer, right, or call it back up. Take the natural logarithm of that number and then do what? Divide by that negative 0.8. So our answer is 10.139, which means after 10 days,
But wait, wasn't it like small number after 5?
exponential though.
54 students were infected after 5 days. 5 additional days, 2,000 students are infected. Okay? So think about that when you choose not to wash your hands.
It does not.
Wash your hands. If you're sick with something contagious, think twice before you go into public places. Here's your homework. You will have a survey. Don't forget your survey.
Yeah.